study the Laplace operator on Rn plus 1 plus. So that is this Rn, and then with y positive. So this is x in Rn. That's what I call Rn plus 1 plus. This variable. And suppose this is equal to 0, and suppose u restrict to the boundary is a given function f. Then the claim is that we observe that this Laplace to the minus 1 help of f on the boundary. So this is Laplace on x variable of f is equal to minus du dy restrict to y equal to 0 at the point x, y. Okay, so and this is a classical result, and that's the Dirichlet to Neumann operator from Dirichlet data to Neumann operator, and that corresponds to Laplace 1 help f at the point x. So to see this, so suppose we denote this by Tf. And then one see that if we look at T of Tf, then this is equal to T of, so I should say my Tf is this thing. I define Tf equal to this, and I claim that this is equal to Laplace 1 help f. So that is T of minus uy. So T means take the normal derivative. So this is the same as uyy. Uyy restrict to y equal to 0. And so this is, because Laplace u is equal to 0, so this is the same as minus Laplace xu. Okay. So if T operates on choice is Laplace on u, and u restrict to the boundary is equal to f, so this is the same as minus Laplace f. And now T operating on choice is Laplace f, so T1 help is equal to u. So that's a classical result of Dirichlet to Neumann operator. So this is the Dirichlet to Neumann operator. Okay. And now, for what the result of Caffarelli and Silvestro is, they extend this result to minus Laplace to the gamma power. Okay. So recall, minus Laplace x f to the gamma power, and if gamma is a number between 1 and 0, and one can define that. There are many ways to define that. One way is to think about that as a Fourier transform of c to the gamma power, the Fourier transform of f, f of c. But one can also define this using the singular integral approach, and that's equal to the integration of f of x minus f of x hat and dx hat of x minus x hat to the n plus 2 gamma power. So one can define it using that. So that's a definition on R integration over Rn, and this is defined for f in h gamma naught. So in that sense, this means gamma derivative in L2. Okay. So function with gamma derivative in L2 is h gamma naught. Okay, and now the theorem of Silvestro and Caffarelli is to say this theorem has an extension. Suppose one begins to talk about divergence of y to the 8th power gradient of u. So this gradient in both x and y, and divergence of that equal to 0, on Rn plus 1 plus. And if you restrict the boundary, it's a given f. Okay. Then their observation is then, if f is a function in H gamma norm, then minus Laplace to the gamma power of f is the same as equal to some constant. I haven't been very careful about the constant limit of y to the y tends to 0 or y to the a du dy. And where a is equal to 1 minus 2 gamma. So given gamma between 1 and 0, and suppose we can treat this minus Laplace gamma f as a boundary function, and the boundary function is a weighted Dirichlet to Neumann operator of the harmonic extension. And actually, their theorem says more. Their theorem says this result, the estimate of the boundary behavior through its harmonic extension, is consequence of the energy identity. So the energy identity is the following. They say that you have that in this case, if one look at the gradient u square of xy, and then y to the eighth power dx dy, and integrate over Rn plus 1 plus. One look at the energy of this PDE, integration multiplied by u on both sides and integrate. And one get this expression, and that says that this is actually equal to the Fourier transform of f hat c squared, and then c to the 2 gamma d c, and c in Rn. That's an actual computation. Okay. And from this computation, one knows this is actually equal to minus Laplace gamma f integration over f over Rn. So one has an energy identity, which is the energy of the boundary function minus Laplace gamma f is through its extension. So that's called extension theorem. So, and in corollary of this, so this is CS extension theorem, and what they really did is they established this identity, and then they say that using a variational method on both sides, think both sides as variational problem, then they identify their Euler-Lagrange equation as variational problem, and that's the first statement. So this statement actually implies that statement. That's the way they prove this extension theorem. And let me point out there's a corollary of this, and which we will use later. And the corollary is one can now think about this minus Laplace gamma f. There is a Sobolev embedding theorem. So the Sobolev embedding says that if you want to have this W gamma 2 derivative function and then embed into L. And now this is 2n over n minus 2 gamma power. Sobolev embedding. So when gamma equal to 1, you get this usual Sobolev embedding. So, but this is for fractional power gamma between 1 and 0. So if we apply that, we get f to the 2n over n minus 2 gamma power, W gamma 2 norm, and then dx, and then we see n over n minus 2 gamma power, and that's then equal to gradient u square of y to the 8th power dx dy on Rn plus 1 plus. There is a constant Cn gamma, So this unit gamma may be different from that constant. And this is for all u with u restrict to the boundary is equal to that. And u doesn't need to satisfy the PDE anymore because the one which satisfies the PDE is the minimum of the energy. So once it's satisfied for this minimum thing, this is true for all u with utility restrict to boundary equal to F. So this is the Sobolev trace inequality. Sobolev trace inequality. Okay. So function defined on the boundary is defined by certain energy in the interior extension in the upper Hell space, but then there is this weight. This weight is 1 minus 2 pi. Okay. So this is the extension theorem of Caparelli and Silvestro. And what is the relation of this to the rest of the thing I'm talking about? So the point of view now we are taking is we have been talking about P2 operator. Then we think about this as conformal Laplace in geometry. A constant n minus 2 over 4 to the n minus 1. Let me use d, dimension constant, on a manifold ND. We have talked about this P2, that's the conformal Laplace operator on a dimension manifold. And then we begin to talk about P4 operator. This is minus Laplace square and plus something, appendix operator, and so on. So it turns out that the GJMS, there is a string of operators operated by Graham, Jenny, Manson, and Sparling, which generalizes this operator to each P2K operator. Where K is an integer. And which is minus Laplace to the K's power and so on. And each of these operator has conformal covariant operator, conformal covariant property. And then this is for k equal to integer. So on Euclidean space, say suppose we are on Euclidean space where G is flat, you do not see all these curvature terms. So the operator you are talking about is just minus Laplace to certain power. So that highly suggests that on Rn, we can also talk about this pseudo-differential operator, minus Laplace to the gamma power. So this operator is a pseudo-differential operator, which is defined by using singular integral or Fourier transform on Rn. And one suggests that there is something in between, a string of operator, and which is all conformal covariant operator of the suitable conformal covariancy. Okay. And which turns out to be the case, and that's this observation, GJMS construct their P2K operator using very constructive method, but there is this paper by Graham and Zosky. In a paper in Invention in around 2005 or something, or maybe 4. They begin to reconstruct the existence of P2K operators through scattering theory. On hyperbolic conformal compact Einstein manifold, hyperbolic manifold. So let me just, it's a whole development, and in doing so, they actually talk about PS operator, where S is in between 2 n and 0. And depending on n is odd or even. Okay. So they talk about this PS operator, where S is a parameter of operator, and when S is equal to 2k, that agrees with the operator constructed by Graham, Jenny, Mason, and Spalding. So so here is a sketch of the series. Very rough sketch. And what I want to say is this operator in the Euclidean case, PS is just minus Laplace to the S over 2 power. But in general, this is a string of operators which has conformal covariant result. Okay. So what is their theory? Let me briefly explain what is going on. So their theory goes like follows. So
there is a question.
yeah.
If the manifold is compact, can't you use the eigen?
Yes, that's coming up. That's coming up. Okay, that's the boundary operator. So it's like in here, we have this situation on boundary. We're thinking of the manifold as a boundary of something which is incompact. Compacting as a boundary of something which is incompact. SM as a boundary of hyperbolic space. That's what I mean. Okay. So here is the definition. Suppose we have an n plus one dimensional manifold and a matrix. And where m is equal to the boundary of x. And where g plus is, and then there's r greater than 0 is a defining function. So dr is 0 on the boundary. Defining function of the manifold. And now, suppose we say that this is a conformally compact. This manifold is conformally compact. If there exists a function R, a distant function, a defining function R, such that this G plus R squared G plus is compact. Okay. So, and this G bar now is defined on xn plus 1 and closure. So this is including this Mn as boundary. So in this definition, as Paul already mentioned, there are many possible choices of the defining function. Once you have one defining function, you can multiply it by other positive function, and still it's a defining function. So this way of defining the compact is compact is modular the conformal class of G plus. Okay. So G plus restricted boundary is defined up to a conformal class. Okay. It's a conformal class of metric. Defines a conformal class of metrics on the boundary of M. Okay. So in this case, Mn is called conformal infinity of xn plus 1. And so we say this is a conformally compact Einstein. If G plus is Einstein. Okay. So that that means VCG plus is equal to a multiple times G plus. But usually we choose this to be conformal Einstein and Poincare Einstein. So that means 3CG plus is minus n times G plus. So the example. So one example I've been talking about is Rn plus 1 plus Rn, and then the metric I'm talking about is dx squared plus dy squared over y squared. And then the G metric, compact metric is y squared, and then is times G plus. This is the Euclidean metric. Restrict to the boundary is the Euclidean metric. Euclidean metric. Okay. So, and that's the example I talk about. Here, it's really the boundary is not compact. But on the other hand, it's conformally to the compact C. So, a model example is the result of contrast to Caparelli and Silvestro. And the real example we have in mind is we talk about the union hyperbolic form. And with the metric, the Poincare metric, GH. Okay. So in that case, we have the sphere Sn as conformal infinity. So what is it? So GH, we can think about it as 2 over 1 minus y squared, and then dy squared. So this is the hyperbolic form. Okay, so hyperbolic form. And now we talk about GH. And then in that case, that's the Poincare form. And in that case, it turns out the natural defining function is dy, which is equal to log of 1 plus y over 1 minus y. So this is the hyperbolic distance from a point y to 0, dy. And then the good defining function, geodesic defining function is equal to 2, 1 minus y over 1 plus y. If one chooses this coordinate, then one can rewrite GH using this coordinate is equal to dr squared plus 1 minus r squared over 2 squared, and then maybe r over 4 squared, and then G canonical metric and r minus 2. Okay. And for GC is the standard metric on S4, on Sn, the surface metric on Sn, the canonical metric on Sn. So in this case, the R squared times GH is my G bar, and G bar restrict to Sn is the given canonical metric GC. So in this case, the sphere is the boundary of this hyperbolic ball, and it's the conformal infinity. So that's the. There are many other examples in mind, and this is a typical example: conformal compact Einstein. So I denote it by CC. And one particular property of CCE metric is it is asymptotically hyperbolic. Asymptotically hyperbolic. Okay. So that means that the metric G bar is the sectional curvature tends to -1 as things tends to the boundary. Okay. As near the boundary, it's asymptotically hyperbolic. And there is a general result. So this is called asymptotic hyperbolic manifold. And there is a result from theory developed by Mazzero, M-A-Z-Z-E-O, and Melrose in around 1987 to 91. What they do is they begin to study on spectrum analysis on asymptotic hyperbolic manifold. And there are lots of many good results, but the key point which is relevant to us is the following. They say in a hyperbolic metric, if one begins to study the spectrum of this hyperbolic Laplace, the spectrum of this on an asymptotic hyperbolic manifold, there is two parts. There is this point spectrum. Okay. And then union is essential spectrum. So point spectrum is those spectrum with L2 eigenfunctions. And then there is the essential spectrum. And the point, so this is I denote by point spectrum. And the point they want to make is there are only finite many point spectra. Okay? So finite many points. So the other all are continuous spectra. So there are finite many exceptional points, maybe finite many exceptional points, and then they begin to talk about except for finite many points on the interval 0 to n squared over 4, you can talk about the Laplace operator being invertible. Okay? So if lambda is not in the point spectrum, except for these finite many points, one begins to talk about this resolvent metric. So it's minus Laplace of G plus minus lambda. But since I want to stress this lambda as a point in 0 to n squared over 4, I write this as s times n minus s. Okay. So except for this, one can study the inverse about this operator. That's called the resolvent operator. One can, this operator is invertible if this point is not a point spectrum. Okay, so of course there are deep theory here, but there is only one result, which is I want to state, and which is a deep result that I want to state. So in this setting, given a function f, okay, in C infinity function on M on the boundary, okay, one begin to talk about something called a Poisson operator. Ps of F. Okay. And we denote it by Us. So Us is a function which solves the Laplace equation minus Su minus S minus N minus Su equal to 0. Okay. And then relation to F is the following. So one look at this equation. Except for finite many points, you can solve. Okay. And the relation of that to F, so U equal to U of S, is the following PDE on xn plus 1. And to solve so, one notice that there are two asymptotic solutions. If I look at this, the G plus operator is hyperbolic operator. So G plus, remember, is equal to R squared G plus is compact. So R is one of the defining functions. And if one look at this, one notice that R to the S and R to the n minus S both are asymptotic solution. So if one look at minus Laplace plus R to the S minus S n minus S R S, that's equal to 0 plus O of R S plus 1, and so on. So both these are approximate solutions. In this asymptotic setting. Okay. And then what the theory, the main result of Melrose and so on, is to say that the general solution U can be written as R to the S power times F plus R to the n minus S times another function H near M, near asymptotic infinity, and with F restrict to the boundary of M is the given F. So this is if S n minus S is not a point vector, then you can solve it. Okay. So that's this equation. So we can solve this Poisson equation or this hyperbolic manifold, and then there's this Poisson equation given at F. And now the key observation of Graham and Zolsky is to say what is the relation of this function F, the given boundary function F, to its behavior, what they call scattering behavior. So the scattering operator S. Okay. So S is an operator. S of S operating on F is defined to be that data H restrict to the boundary M. Okay. That's called the scattering operator. Okay. So S equal to H equal to this. And so the key observation is one has this, the S operator, SS operator has pre-simple as a pseudo-differential operator. The pre-simple is minus Laplace of G bar restrict to the boundary to the S power. Okay. S minus n over 2 power, and so on. Okay. One can compute the pre-simple symbol of this operator as Laplace. This G naught is G bar restrict to the boundary. Okay. So one knows the leading symbol of that is this. And then another very important property for us is S of G. If one look at the conformal change of G hat of S, so you given this G naught, G bar, you can change it to E to WG, and that I call G hat. The G bar to this G hat. And G hat also can restrict to the boundary. It turns out this S of S operator, because all this is defined through a choice of this distance function. So if you're changing the metric from G to G hat, it amounts to changing R to R hat, which is equal to E to W R, EW times R. Okay. So that means that you can also define the scattering using this parameter R hat instead of R. And they are the same operator. So that means they have the conformal change property S of change of variable, and that change of variable is like changing R to R hat, and if you write it down, this. Okay. So that means conformal covariant problem. So, and then through this observation, Graham and Zalsky say the third important property is to say, now, this is the Penney's operator, GJMS operator we talk about when S is a good integer. Okay. So the next thing is SS has a simple pole at the point S equal to n over 2 plus k, and where k is an integer. And then the PJ2k operator, the GJ and S operator is up to a constant, the same ck times the residue of this operator S of S at the point S equal to n over 2 plus k. So in general, when S is not n over 2 plus k, you have a pseudo-differential operator. At the point S equal to n over 2 plus k, you get a differential operator. And that differential operator also has the leading symbol minus Laplace to the kth power, and that's the P2K GJMS operator. Operator. So in that way, we capture the GJMS operator. Okay. But the advantage of putting all these things in the setting is actually it justifies Bronson's point of view of this class of operator. Remember that we talk about P2K and we talk about Laplace defined on dimension, and with that dimension n tends to 2. And we don't know what that means. But this setting really says the whole thing, the integer is just a special point of a continuous spectrum. Okay? So there's this S parameter, and then you can let S tends to this integer, it becomes P2K. So all this Bronson's point of view can be put in this frame, and there's a continuous parameter. So now, let me come back to this thing. So in particular, I'm interested in the study of, so in particular, we have this P2 gamma operator when gamma is between 1 and 0. And the P2 gamma operator has conformal covariant property. Of this index where S equal to n over 2 plus gamma. This is defined to be the S of n over 2 plus gamma. And the leading symbol of this operator is minus Laplace to the gamma power. Okay. So this is the operator. And on the Euclidean space, this P2 gamma is nothing but the Caffarelli's operator, or this Laplace operator to the gamma power, and X variable on gamma power. So we capture this class of operator, the extension theory.
But when gamma is not an integer, then this thing will not have a pole. It is just a value. So only poles at this point.
Yeah, the only pole is at
n over
k,
2
n
plus.
over 2 plus k. And in general, it's a meromorphic function. Only at pole, at the single pole, at k. And there you get a differential.
And the other thing is, can you read Q curvature out of this? The value of Q curvature, can you read it out of this data?
Yes, you did. You
You
did.
can.
You completely recapture it. This P2K is our P2K, and Q curvature is our Q curvature. And each comes
So, no,
from
but
the
in
set.
terms of the scattering data, is there what do you know offhand what the formula is for Q curvature in terms of
Yes,
scattering data?
Let's be careful. Okay? Here, this is M.
Right.
Okay, and then there is X. When you talk about this Penny's operator, you can think about either this Penny's operator, like my P2 gamma, is a boundary operator. The definition of that depending on the extension inside. Okay. So this G plus and then the G bar restrict to the boundary decides this class of operator. It's a conformal covariant operator. Only on K equal to integer, you have an operator which is really defined on M. It becomes a differential operator. The pseudo-differential operator depends on the extension inside. That's the picture. But of course, you on X, you can also talk about its own Penny's operator and so on. But at this moment, we treat M as a boundary of X. You have P2 on X, also P2 on M. But I'm talking about P2 gamma on M. And this is depending on the extension inside.
Yeah, but my question was whether there is a offhand a formula for the Q curvature for the boundary operator.
I'm going to talk about that. We know very little about it. We know that's what I'm going to talk about.
In terms of F and H and so on, that was
Yeah. You don't know that. You don't know much about what is Q for this class of P2 gamma operator. But the special number gamma equal to integer in N over 2 is plus K, you do. And then also at say gamma equal to 1/12. We have Dirichlet Horner operator, and then this Q is neutral.
Yeah, because the only thing is that in the theory of spherical functions, Harishchandra had a similar theory for constructing the C function.
Say that again?
In the theory of spherical functions,
Yes.
there is a theory of Harishchandra for constructing this invariant C function.
Yes.
And it is, I think, known to maybe some people that this C function has to do with Q curvature. So there is some link that seems to be, you are also suggesting.
Yes. Yeah.
I mean, there is some connection.
That's right.
And it needs to be probably written.
At this moment, I have to say that the picture of the operator on the boundary and the operator on the interior is not entirely clear at this moment. Okay?
Certainly not for
Yes, that's right. Only in these very special cases you can write it down. So, but there is one result I want to talk about, and this is the following thing. And what I'm trying to do now is this whole picture suggests the question I have discussed in detail. Remember, in the last two lectures, we are trying to see on 4 manifold, there is this operator, when is this positive? The positivity of this, depending on some Q curvature, if Q4 is positive, and if this a scalar curvature is positive, then on this 4 manifold, Q4 is positive. Okay. And this whole frame plus Caparelli's extension theorem suggests that maybe this is part of the general phenomenon. Okay? So we like to study positivity of this P2 gamma operator in terms of some curvature invariant, and this curvature is defined. Okay? So there is in this general setting, let me say that a very limited thing we know about. Okay? So that means that in studying of this, we use many special knowledge and about what does P4 look like, what does Q4 look like, and a lot of geometry. And here, this says everything is from a PDE, and maybe we can understand the thing through extension theory. That's what I'm trying to say. So, but this is just something one wish to happen, and there's limited progress. And let me say that what we know now. So first, let's do a translation. So this is an observation by Michel and Gonzalez. So this is an article which published in Advances in Math last year. 1-2 or something. So what we do is we begin to translate this result, the Poisson equation. So on xn plus 1, mn and g plus, this CCE setting. So hyperbolic setting. And if we look at this Poisson equation, given an f, and this is on xn plus 1, the Poisson equation, and u, we know is something like r to the s power times f plus r to the n minus s times h, and f is given. Look at this equation. Okay. And then the edge of the restricted boundary is what we call the S operator at the index gamma f, where S is equal to n over 2 plus gamma. That's the setting of CCE setting. Okay. And then we can translate this PDE to a PDE with respect to G bar. Notice that this G bar and G plus is just by some suitable distance function R squared, which we can choose. So G bar is conformal to G plus. And the advantage of G bar now is in a compact setting. Okay? So we can use this conformal covariant property or conformal Laplace to translate this equation to G bar. Okay? So that's what we have done. So the G bar operator, you translate, it becomes minus diversion of r to the eighth power gradient of G bar of u, and plus some function which is e of r and a times u equal to 0. Okay. And this a turns out to be 1 minus 2 gamma. And this capital U is equal to r, I'm sorry, in my notes I have n minus s and rs. This index s and n minus s are dual index, so there are different ways of writing it. So maybe make my notation consistent that we might write n minus s and s. S and n minus s are dual index. One can write it one way or the other. So, but let me write this way. And then this f is, capital U is just r to the s to the n times little u. Okay, so this u restrict to the boundary is my f. Because I know capital F restrict to the boundary is my f. Okay. So this is equal to the data. So now we have the second order PDE with a weight. That weight is r to the h power, and then it's an error term. Let me say a little bit about that error term later. And then, in this case, u is a Dirichlet problem. On the boundary is equal to f. We are solving this equation, translating into a Dirichlet problem, and then this operator S gamma f become the Neumann condition. Okay. And the S gamma of f, now this is equal to this h restrict to the boundary. One can write it down. It's like Caffarelli's notation. C, there's a constant, and then limit r tends to 0 of Ra and du dr. Okay, so one can write this. So we can translate this using to this, and by the conformal transformation law of Laplace conformal Laplace. So these two are equivalent. Okay? So this is if and only if this operator. Okay? And it turns out that the way to write this is this advantage of that is this translation is true for all gamma between n over 2 to 0. Okay? So in the original work of Caffarelli, they deal with gamma between 1 and 0. But this translation, there's no reason it's not to be true beyond n over 2. So this is true for all gamma between this. And this equality holds between gamma between 1 and 0. And when gamma is between 2 and 0, you can also identify the boundary operator. Okay? So there's when gamma is between 2 and 1, you can also write down this, and the formula is a little bit more complicated. So it's not important for this lecture. This would become limit r tends to 0, r to the a0 power ddr, or is r minus. There's an expression of this. I don't want to go into the dd gamma of u and so on. Okay. This a0 is equal to 1 minus 2 times gamma minus gamma. So it's in our paper. One can write it down. Okay. So if it's gamma between 2 to 1, you have one more derivative and so on. One can identify the boundary operator in general. Okay, so at least let me write down a theorem. So from there, one can apply this Caffarelli's Silvestros's extension theorem and get a conclusion. Let me say what is an application. So there are two applications of this parallel trace.
Your theorem follows also have the identity.
Yes, that's coming up. That's
and
coming up
energy
now.
identity.
And there's energy identity. There's energy identity, but I haven't quite told you what that is. Okay, so there's an arrow turn and then energy identity.
So this comes from the curvature.
Yes. This by integration U on both sides and then energy identity. So as an application, one have two applications, and the first one is done by Chang and Gonzalez. What they did is they used this to study prescribing Q curvature problem. So when gamma is between 1 and 0. Okay. So suppose I want to study this operator Q2 gamma of F equal to a constant Q2 gamma, and then F to send n plus 2 gamma over n minus 2 gamma power for the metric G, which is equal to F to the 4 over n minus 2 to the n minus 4 over n minus 2 gamma power times 2. And now this is the Q gamma curvature by definition. Okay. So one can try to study now gamma is a fractional power. And then one wants to study when can you deform this thing to Q2 gamma equal to constant in the same conformal class. So instead of a differential operator, you now have a pseudo differential operator. And then it used to be we do not know how to handle this problem because it's not clear what is the energy on this boundary operator P2 gamma FF. But using this concept of this extension, so the boundary operator here the suitable extension is like Caffarelli-Silvestro's energy, which is on xn plus 1. And then one also has a Sobolev trace inequality, and using that inequality, they begin to say they have partial result saying when can you deform this Q2 gamma equal to constant. And this program is far from finished. They have been able to handle certain cases. There's positive mass and so on. Used to be this problem, you can only deal when the manifold is for Poincare series. Okay. So an axis is n plus 1 or coaching a group. And you can deal this using this group structure to handle this problem. And now this can be done for this whole CCE set. And this is for gamma between 1 and 0.
Suppose you're taking the manifold is H mod gamma, right?
Yes.
Suppose gamma is coming from a number theory. Some
Gamma is
coming from number some modular groups. Number theory groups.
I see. Yeah.
Does Q2 gamma has some number theory?
Yes. Yes. This thing has something to do with the Poincare exponent of that group. And when that exponent has certain index, you can try to solve it.
So for example, if you take H mod SL2Z across this, in that case, can you say something here?
Say that again.
Take the across space
Yes.
and modulo the SL2Z.
I don't know.
I mean,
Yeah. There
they
must
are
be
modular
such a
for-
general setting, but yeah. Ching first deal with it when for certain type of compact or group, and then he did this for this general setting.
I mean, you can go for finite volume also. You can go for finite volume manifolds or compact.
In this case, I think he only deal with compact quantities. Okay. Now there's the second application. The second application is a result of this kind. Let me state the theorem. This theorem is stated in completely different language by Bilabu and Qin, but it's equivalent to the following statement. They use scattering port terminology in scattering theory to state this theorem. But the statement is the following. Say if this manifold so we have this CCE setting. And suppose this metric restrict to the boundary, I call it G, has Yamabe of Mg positive. So the boundary metric is positive scalar coverage. Then we can improve. This would imply this P2 gamma operator is positive for each gamma between 1 and 0. So starting with something whose boundary is Yamabe class. So that means the conformal Laplace is positive. Positive operator. The second order differential operator is positive. But if it's already CCE setting, you have this class of pseudo differential operator, then it's all positive. It's all positive. So now let me give a proof of this result. This proof is a little bit different from the proof of Qin and Bilamu. So the proof of this uses the following two facts. So I will sketch the proof of this, but let me first remark that at this moment, this result is all between gamma between 1 and 0. It turns out that the extension theorem of Caffarelli and Silvestro and so on, and also on CCE setting, can be done between gamma between n over 2 and 0. Okay. But the energy term when gamma between 1 and 0, the energy term is this gradient u squared to the y to the 8th power. The a is 1 minus 2 gamma. That's the energy term when gamma is between 1 and 0. It turns out that for gamma between 1 and 2, the suitable energy term is Laplace u to some power. So the energy term, so this is equal to this P2 gamma f in the energy f. And for the same result to hold, even on this Euclidean space, the energy term is Laplace u squared y to the b's power, where b is 3 minus 2 gamma. Okay, and this is a work of Ray Young in the Euclidean case. And then on the CCE setting, there's a recent work by myself and Jeffrey Case. We are developing the whole series of the extension theorem for between gamma high index. So the point I want to make is, it turns out when gamma is between 2 and 1, for example, we talk about e.g. when gamma equal to 3 over 2. So in that case, P2 gamma operator is P3. A third order pseudo differential operator on boundary of a manifold, on boundary of M. So it's a third order pseudo differential operator, and this result tells you the suitable energy of the third order operator, the extension, is the fourth order Penny's operator on xn plus 1. Okay, so it's the energy term is the Penny's operator. And so on. Okay. I will not go into detail, but there is a work, and it turns out these Penny's operator do occur very naturally in this setting, and that treats as the energy of some P2 gamma operator. Now, with the rest of 10 minutes, let me at least sketch the proof of one theorem, and that's the theorem. Sketch the proof of this theorem. So for this theorem, one of the key steps, the key proposition, which is a proposition also used in the original proof of Ching and Dilamu, is a result of JFD. And what he is trying to prove is, he said that in this setting, he is trying to say, if the Yamabe constant of this G is positive, on the boundary is called G. If that is positive, then his result says that there is no exceptional point of point spectrum. Then it's empty. There is no exceptional point. Remember, from n squared over 4, there is this lambda, there is finite point, there are examples where the point spectrum actually exists. But he said that if the scalar curvature on the boundary is positive, the scattering metric does not have point spectrum. Laplace for this Laplace operator is empty. That's his theorem. Okay. But in the strategy of his theorem, he introduced something which is still a mysterious thing to us. Okay. And the key lemma is the following. consider a function which is, he look at its operator Laplace U, and he look at the linearized Yamabe operator of minus Laplace on this U. So he look at its n plus 1 U. Okay. So he said that on xn plus 1, we look at this. So this corresponds to s equal to n plus 1 for solution. So this is s n minus Poisson operator, s n minus s, and s corresponds to n plus 1. So he look at this operator, and then this operator, he begins to write down its asymptotic behavior. U is equal to 1 over r plus r, and then there is this constant, and that constant is a scalar curvature of G. And then plus, there's a dimension constant, scalar curvature of G and R, and so on. He said that given a distance function, one can solve this PDE and with asymptotic behavior like this. That's the theorem. And then he used this to construct barrier to say this is empty. And where does this PDE come from? This is a linearized equation for the Yamabe equation, but let me not go into this because it's still mysterious to me why he considered it. Now, the next observation is the following. For any function, scalar curvature of u minus 2 g plus. So u is a positive function. And since this u, the leading order term is 1 over the distance. So the natural net compactification is u minus 2 g plus. And if we compute this compactification, then this is n times n plus 1, and then u squared minus gradient plus u squared. This is always true. And now, for this particular u, if one knows its asymptotic behavior near m, one can compute this ru plus minus gradient plus u squared near m. So one can see that this scalar curvature restrict to the manifold is pickup or multiple of the scalar curvature on the boundary. Is a multiple of the scalar curvature on the boundary. Okay, so this is so maybe I use G naught to know it's the boundary. So the scalar curvature on the boundary is the original scalar curvature, and with our assumption, we assume it's positive. Then there's a magic computation. One begins to compute a plus of the scalar curvature. This guy is true in general, this identity. Nothing to do with the PDE. But using the PDE, one can compute the Laplace of R. And this expression is so simple. So compute Laplace plus of the scalar curvature is nothing but a Buckner formula. Okay. So it's completely computable. It turns out that this is just hashing plus of u minus u squared. And anyway, the point I want to say it is as a sign. Okay. So this operator, the minus Laplace is equal to this constant 2 here and has a sign. So the conclusion here is hence this G, the Jacobi metric u minus 2 G plus has scalar curvature of GL positive. Okay. So this Laplace is positive, so minus this is a plus, minus, a plus plus I is negative. And on the boundary, it's already positive, and the interior is positive. So this has positive scalar curvature. And then, from there, that's the key observation. The key observation is, if the boundary metric has scalar curvature positive, then the interior also you can construct a metric which is positive. Actually, this simple observation leads to a simple proof of a result of Yao and Witten. Okay. Yao and Witten has a theorem which says if in this setting the boundary metric has positive Yamabe class, then the boundary manifold has to be simply connected, one connected component. Okay. And use this observation, one can give a quick proof that okay, there is only one end of this positive Yamabe metric. So one can see the boundary has only one connected component. So that's a result of Jack-Lee. So that's step one. And then what we do is we have step two is we begin to use the extension theorem. Following that answer your question, do we have the extension theorem on CCE setting of Caparelli and Sylvester? Yes, we do. And then in that case, the conformal in this extension theorem, we are allowed to choose any compactification. So the metric 1G plus one should choose is this Jack-Lee metric G plus. Okay. We use this extension. This extension has the advantage that this scalar curvature is constant. Okay. So in that case, one can compute this U, this arrow term. Remember in the extension, I have this arrow term U, and it turns out that arrow term times this A, where A is 1 minus 2 gamma. This arrow term, I have this minus divergence, and R to the 8th power, my R is UL to the 8th power, and then this is gradient U, and plus this arrow term. That's my extension, which captures my boundary equal to 0. And in that case, this UL is so nice. It satisfies this simple linear PDE. One can compute this arrow term is a positive constant depending on A times the scalar curvature of G bar. Just simple thing like that. Okay? So this is positive. The only observation is this is positive. So you have this PDE and whose behavior on the boundary is equal to F. We know its Neumann data gives you P2 gamma F. P2 gamma F is just the Neumann data of limit R to the 8th power is R is UL to the minus 8th power and DUD. This means R is UL. It's UL is like R. UL inverse is like R. So this limit of this is equal to this as R tends to 0. So one can compute to see P2 gamma FF. The energy term of that is integration of this multiplied by U, and you capture that boundary term, and that's always positive. Okay, so we have the energy identity. You get P2 gamma FF. This is 5. This P2 gamma FF. On the boundary, integration of the boundary is equal to this energy term, this gradient U squared, and now it's UL to the minus 8th power, and then plus, so this EUL is CA, and then there's this integration of this G bar and this Jack-Lee matrix square, U square, and then this UL to the minus 8th power. That's the integration over X. So everything is positive. for all u. Okay? And that shows this operator is positive. So this extension theorem and view like this gives you an alternative way of visualize when is this operator positive. And so that's, I have used up my time, and thank you for listening. By the way, here I only talk about CC setting and hyperbolic manifold. There are lots of generalization of this Caparelli, Silvestros, extension theorem in different settings. There are lots of results in settings.